Let's imagine the internet is just a massive 8-lane superhighway, and your firewall? That's the central toll plaza that every single car has to get through. Now, what if that plaza had to handle millions of cars a second without causing a citywide gridlock? That's the reality for modern firewalls. So how in the world do they keep this digital highway from becoming one giant permanent traffic jam? Well, let's dive in.
It's a huge problem, and it was solved with a really brilliant piece of engineering called CoreXL. And honestly, understanding it is like learning the secret to managing the busiest traffic jam on the planet.
So you gotta go back in time a bit. Firewalls used to work like that highway having only one single toll booth open. Every packet of data, I don't care how small or simple, had to line up and get inspected by one processor core. As you can probably guess, this created an absolutely massive bottleneck. Now, the technical reason for this jam was this thing called a monolithic lock. In our highway analogy, this means that to inspect just one car, the single toll booth operator had to lock down the entire plaza. No other cars could even move until that one inspection was totally done. I mean, sure, it was secure, but it was incredibly inefficient. Right around this time, the whole tech industry had a huge shift. Chip makers basically hit a wall. They just couldn't physically make a single processor core run any faster. So the new game was to put multiple cores, multiple brains, onto a single chip. This was awesome for general computing, but for our firewall with its one toll booth problem, it just meant we had a bunch of extra workers standing around with nothing to do. So CheckPoint came up with this really brilliant two-step solution. First, they figured out how to open up way more toll booths. And second, they hired a really smart traffic director to manage the whole flow. Let's look at that first part. That first step was to create what's called a firewall instance. You can think of this as a complete, independent copy of the entire firewall, running on its very own dedicated processor core. So in our analogy, it's just like opening up several new, fully equipped toll booths, each with its own staff and its own rulebook. But look, just opening more lanes is only half the battle, right? If you just let all the cars swerve into any open lane they want, you'd have absolute chaos. You need an intelligent traffic cop to direct everyone. And in CoreXL, that traffic cop is called the dispatcher. So, let's follow the journey of the very first packet from a brand new connection. It shows up, and the dispatcher checks its master list and goes, never seen this conversation before. So it just makes a quick choice and sends the packet to an open toll booth. Let's call it Worker 2. Then Worker 2 inspects it, and if it's all good, it tells the dispatcher, hey, I've got this one. From now on, you send all traffic related to this conversation my way. And this gets us to a really crucial concept called stickiness. The dispatcher's main job is to make absolutely sure that once a conversation starts with one firewall instance, one toll booth, every single packet from that same conversation goes to the exact same instance. This is absolutely critical for performance. This whole system gives you 3 huge wins. First, you get parallel processing, multiple toll booths handling different cars all at the same time. Second, you get that connection stickiness, which stops conversations from getting all scrambled. And third, you get something called data locality. This just means all the info for one conversation stays right there in that one core super fast local memory, its cache, which makes every check after that almost instantaneous. But you know what? We can make this system even faster. Think about all that trusted everyday traffic. Does it really need a full, deep inspection every single time? Nope. And that's where the next layer, SecureXL, comes into play. Just think of it as this firewall's express lane. We call this the fast path. Once a conversation is up and running and we know it's safe, SecureXL basically flags it. And from then on, packets from that connection just get waved right through the express lane. They don't even have to slow down for a toll booth. This just massively speeds up all that trusted traffic. Then, of course, you've got the slow path. This is the standard route we've been talking about for any brand new or maybe suspicious connection. This traffic gets directed by our dispatcher over to a firewall instance, one of our toll booths, for a complete top-to-bottom security inspection. Yeah, it's slower, but it's how you catch the bad guys. And this is where it gets really clever. There's also a medium path. What if a connection is trusted, but you still want to do a quick spot check for something specific, like an intrusion prevention system signature? Well, this traffic gets to use a special lane. It bypasses the main toll booth inspection, but gets a quick, specialized check before going on its way. It is the perfect balance of speed and security.
So let's put it all together. You've got SecureXL, that's your express lane for trusted traffic. You've got the dispatcher, that's your smart traffic cop directing everything. And you have the firewall instances, which are the individual inspection booths for anything that needs a closer look. Together, they turn what could be a total traffic nightmare into a free-flowing system.
And the system is even more flexible than that. With something called Core Affinity, an administrator can actually go in and manually assign roles. So if the dispatcher, our main traffic cop, is getting overwhelmed, you can assign a second or even a third CPU core to help it out. It's exactly like putting your best officers on the busiest intersection during rush hour. So this whole multi-layered, intelligent system is how we manage the chaos of today's internet. It's a brilliant solution that was literally born from the physical limits of a single processor. And that leaves us with a really fascinating question to think about. As data speeds continue to explode and threats get even more complex, what's the next bottleneck going to be? And what will the next generation of digital traffic management even look like?